So I'm Marco. This is joint work with Samir Singh and Carlos Gestring at the University of Washington, where we tried to show that you can understand what any classifier is doing and that's really useful. So let me get started. Machine learning applications are becoming pervasive. There are assistants now. They're driving our cars. They're ruining board games for us. They're basically doing stuff. And what do you do if you want to build a machine learning application? You might think that the pipeline looks something like this. You have some data. You want to arrive at some application. So what you do is you train a machine learning model, be it a deep neural network, random forest, whatever. And then from that model, you get predictions, and you make decisions. And those interact with your application. Now, there's a crucial step missing in this pipeline here, even though this is what most people think about when they think of machine learning. And that is, what if my predictions and decisions do not make any sense? I could get fired, or even worse, I could get sued. So we call this the trust challenge. How do I know if my model is behaving as I expect it to? And how can I convince myself and others, for example, my boss or someone who wants to use my product? How do we know that they're working? They're obviously very popular nowadays, deep neural networks, and it's a challenge. We obviously can't go inspecting their neurons, so they're very opaque. So this trust problem is really fundamental. In a sense, every time you deploy a machine learning model, you are trusting it implicitly. And it's been studied a little bit, and there's a particular kind of problem that Netflix faces, for example. Not only do they have to trust the model themselves, they have to get us to trust it. So if I'm going to spend 2 hours watching a movie, I better have a good reason for it. And I'm not going to watch it just because Netflix said so. So what they do is they show a kind of explanation where they say, oh, you're going to like this movie because you like these other 3 movies that we also recommended to you. So the user builds trust in the system. The doctor case is also really interesting. We've been trying to apply machine learning to medicine for a while now. But obviously, if we just tell a doctor, look, you have to cut this patient open because the model said so with probability 90%, that doctor is not going to do anything. And maybe we don't want it to. So if instead we tell the doctor, look, you have to open this patient because look at this symptom, look at this similar case, it's much more likely that the doctor is going to use machine learning to make better decisions. Finally, if we understand our models, it becomes much easier to improve them. So if we can understand what they're doing, we can fix problems, we can do better model selection, we can do better feature engineering. So obviously, we do trust machine learning. I just said that they're everywhere. So what do people usually do to gain trust? How do people solve this problem? There are basically 4 ways that people do. First way is what I call interpretable models. And that just means restricting ourselves to using models that are easy to interpret, like a really short decision tree. And this has a lot of traction in domains like medicine, where we really have a constraint on understanding what the model is doing. And this is a promising approach, but often we do this at the expense of accuracy. You obviously cannot use a deep neural network for this. And the tragic part of it is that in order to make these models more accurate, we basically make them uninterpretable. So we say, oh, 1 decision tree is not enough. Let's get 1,000 decision trees to do the job for us. And then we don't know what they're doing anymore. Second thing, and maybe what most people do, is they measure accuracy on some held out data or cross-validation. And this is great. We should keep on doing this. But there are many pitfalls. And I'm just going to show you one example. We have this data set called 20 news groups, where people have been optimizing algorithms on it for the last 20 or 25 years or so. And we just took a subset of this data set. We're trying to distinguish between emails sent to an atheism news group or Christianity. And this is supposed to be a hard problem, because atheism and Christianity share a lot of words. So it should be hard to distinguish between them. And then we train any off-the-shelf machine learning classifier on this data set. And we instantly get 94% accuracy. So you think, oh, the triumph of machine learning. Machine learning is great. We can solve this hard problem immediately. Well, not so fast. If you look at the predictions and understand what they're doing, you'll notice that a lot of predictions are due to features like email addresses or names. In this particular data set, you have some people who always post on the same news groups. So instead of building a classifier that's distinguishing between the topics, a lot of times you're just distinguishing between who's sending the emails. And that's not very useful at all. In fact, we recently got a new data set for this task of distinguishing between atheism and Christianity documents, and applied this classifier that has 94% accuracy to it. We got 57% accuracy. And if you think of that as a real world, that's really embarrassing. You train a classifier, you go to your boss and say, look, I have 94% accuracy. And then you apply it in the real world, and it sucks. And that's really embarrassing. And this is one problem that happens, but there are plenty of pitfalls that you can fall into when you're doing accuracy. I just want to highlight one that's called data leaking, where it's really hard to avoid. Some of the data that you're trying to predict leaks into the features you're using. So sometimes you're looking into the future or things like that. So instead of looking at accuracy, what a lot of people do is, the obvious thing is they do A/B testing. So I want to know how it's going to work in the real world. Let me apply it to the real world and see how it works. And this is great. It's almost a gold standard. The problem is that it's pretty expensive. Every time you want to do a little change, you have to do an A/B test. It also, you potentially expose users to really embarrassing models. Again, what if I get sued because someone on my A/B test was discriminated against by my model or something like that? And it's also tricky. There's a bunch of research papers that highlight all of the pitfalls you can fall into, even in doing A/B testing. And finally, what people do is what I call voodoo, or I know what I'm doing. I've done this before. And it seems that a lot of people rely on this. And some people are really good at voodoo. Those are the people you want to hire. But we don't want to be relying on voodoo to trust our models. So what we're proposing instead, well, maybe not instead, in addition to looking at accuracy, doing A/B tests, and things like that, and voodoo, I mean, we can't discard voodoo, is that we're going to be explaining individual predictions. So you have a classifier. We're going to make any model interpretable by explaining its predictions. And we don't want to restrict ourselves to using interpretable models. We want to be able to explain any model. So this is what an explanation looks like, just to give you a feeling for it. This is an example from that religion problem that I was talking about. It's an email. It obviously is about Christianity. The guy is saying that Christianity is the one true religion. And we take that 94% accuracy classifier and get a prediction on this. And this is what it does. It thinks that this is about atheism. And immediately, you, the analyst, you're obviously puzzled. Like, why is it doing this? Can I not trust this model anymore? I already told you that you can't trust it. But if you just saw this example, what would you do? How would you fix this? It's not obvious. But if you look at an explanation, and I'm going to show you an explanation there on the right, this is what the model is thinking, as it were. So as evidence for Christianity, it sees the word Christianity. OK, that makes a lot of sense. If you have Christianity in uppercase, that is indicator of Christianity. But as evidence for atheism, it has the following words: posting, host, and keef. And a few other words that are not that important. So why did this happen? It becomes clear that the model is not doing anything sensible. We, as humans, know that we have prior knowledge about atheism and Christianity. And we know that posting, host, and keef should not be words that are being used to discriminate between the two. In fact, when you take a deep dive into the data set, you notice that posting and host appear a lot on the training data, and almost always in the class atheism. It's just one of those things that they got the data in a weird way. Keef, I guess is pretty interesting, is the name of a guy who posts a lot in atheism. So he liked to talk about atheism a lot, but he never posted in Christianity. So for this particular data set, keef is a perfect predictor. If you see keef in the email, it's going to be about atheism. Obviously, this will not generalize, and we should not trust this model. But I hope I've convinced you that looking at an explanation, you can understand that, you get an insight, and you know what to do to fix it. All right. So there are three things that an explanation must have for it to be useful. The first one is that it has to be interpretable. If I'm explaining something in a way that you can't understand, then I'm not really explaining it. And if you think of really long decision tree, like with thousands of nodes, that's definitely not interpretable. But a short decision tree used for an explanation is potentially interpretable. Second thing is that it has to be faithful. Obviously, I'm not going to be giving you the model itself, because that's uninterpretable. So I'm going to be giving you some surrogate, some approximation. But that approximation has to describe how the model is actually behaving. So if we have this 2D example here, and we learn a model on it, let's say we want to approximate it by this line. It's not faithful at all. So if it's not faithful, it's not going to be useful as an explanation. Finally, we want it to be model agnostic. We want to be able to explain any machine learning model. We want to be able to explain models that we're going to invent next year. And we want to be able to compare between models as well. And so we can explain this mess. So our solution to this is what we call LIME. It's short for local interpretable model agnostic explanations. I already talked about interpretable, model agnostic, and explanations, so the local is the only part that I have to explain. Here are the key ideas. First, we're going to pick a model class that's interpretable by humans, be it a line, shallow decision tree, sparse features. And then we're going to approximate that black box model using this model. Now, I already gave you some intuition. That's not going to be globally faithful. If I can approximate my neural network by a linear model, then I should just be using a linear model. But the key insight is that even though it may be really hard to approximate a black box model by a simple one globally, it may be easy to do it locally. So here's just for some intuition, a 2D example where we have some really complicated decision function, obviously not linear, and we want to approximate it by a linear function. Any linear function is going to be a terrible global approximation. But if I just want to explain that red cross over there, then a linear model becomes pretty good. Close to that red dot, the model is approximately linear. And this is something that we expect for machine learning models for various reasons. So that boundary is locally faithful. It's corresponding to how the model behaves close to that example. And that's a good explanation for that particular prediction, not for the model as a whole. So this is how we get these explanations. It's pretty simple. So we have a point we want to explain, the red cross over there. We sample a bunch of points around it, either by perturbing that point or some other method. And we get predictions from the black box model. So the predictions in this case are either red or blue. And then the thing is, intuitively, we don't care as much if our approximation is not as good really far from that point. We care about it being good close to that point. So we weigh those samples by how close they are to the original point. And finally, we learn a simple model on those weighted samples and use that to explain. Now, I said that explanations have to be interpretable. What do we do if our model uses features that are themselves not interpretable? So we could be learning a model on word embeddings, for example. It would be no use if I told you, oh, I think this is about atheism because of this dimension in the embedding. It doesn't make any sense to humans. So we have this notion of interpretable representations. And this just means that we have a representation for the data that humans can understand. And in the case of text, that could be words. And this is the representation that we perturb, and this is what we use to explain. So even if a model is using underneath some word embeddings, we're going to explain it using words, which makes sense to humans. For images, this is what it looks like. Most algorithms will do a pixel-based representation where you have 3 color channels per pixel. And that's hard for humans to comprehend. Like, there's too much blue in this pixel. It's not that intuitive. So what we do is we break the image down into contiguous superpixels. And that's what we use to explain. That's what we perturb. So a more concrete example of the sampling process I illustrated before, I'm going to show you it now with images. We have this original image, which is a bit of a tricky image, because usually dogs do not play guitar. But anyway, we want to get predictions on it. And our model, a deep neural network, thinks that the probability of a Labrador being in this picture is 21%. And we want to understand why. So what we do is we perturb that image in various ways. For images, what we do is hide the superpixels in the image. So we get some perturbed image, and we get a prediction. So if we hide the guitar, the model thinks it's a Labrador, because basically all that's left is the dog's face. But if we hide the dog's face, it thinks there's no Labrador there. And we do this multiple times until we get a data set of perturbed instances and predictions. We feed that data set into an interpretable model. And I already told you we're using locally weighted models. In this case, just locally weighted regression. And from that model, we can easily get an explanation. Now, these explanations we're seeing are really good to getting insights. And an illustration of that is this example I just showed you. We're explaining Google's Inception neural network, which is a pretty opaque model. And the top predicted class for it is electric guitar, with probability 32%. Now, that's a bit puzzling, because what we have in the image is an acoustic guitar, not an electric one. And you should wonder, like, should I trust this model? It's making a mistake. If you look at the explanation, it starts to make a little bit more sense. That part of the guitar does look like an electric guitar. So even though it is a mistake, it's not an egregious mistake. The model is not doing something completely ridiculous. The second class that the model thinks is with the highest probability is acoustic guitar. And the explanation also makes sense. It looks at the body of the guitar. And the third one I already showed you, Labrador, probability 21%. It's the dog's face. So this is a really tricky instance. And we understand why the model makes a mistake. Now, we're from the University of Washington. And our mascot is a husky. And we want to let people bring huskies to the games. But we don't want to let them bring wolves to the games, because wolves could kill thousands of people. So we trained this neural network we're going to have a camera at the stadium that's going to be seeing if people are bringing wolves or huskies. And we trained this neural network, and it has really high accuracy. It only makes one mistake. And we're OK if sometimes a wolf gets into the stadium. Just we don't want it to happen often, because we don't want to get sued. So this neural network only makes one mistake. And we have the following question. Do you trust this model? And what do you think this model is doing? Like, how can it solve this hard problem? Wolves and huskies look a lot alike. So we asked a bunch of machine learning people this question. And it's a bit of a trick question, because if you look at the explanations, now they didn't say explanations at first, but if you look at the explanations, you notice that the neural network is only looking at the background of the image. It's only, we've actually built a great snow detector. So if there's snow in the image, it always predicts wolf. If there's not snow, it always predicts husky. And in Seattle, it doesn't snow much. It almost never snows. So we're going to be letting wolves into the stadium and thousands of people are getting killed. We should not trust this model. So we were wondering, are machine learning people going to notice this egregious problem? And we show them predictions before explanations and after explanations. And we measure two things. One, did they trust the model? And two, did they get the insight that snow might be a problem, that the model might be detecting snow? And before seeing explanation, we showed them 10 predictions. And 60% of them did not trust the model, which is good. You should not trust the model after seeing 10 predictions. But it's a bit scary that 40% of them did trust the model. And I understand. We're machine learning people. We want our models to work. We tend to believe that they are working. What's more interesting is the reasoning. When asked why they thought the models were working, they invented all kinds of reasons. And we do this all the time. So they're like, oh, it's the dog's face, it's the dog's nose, things like that. Less than half of them got this no insight. After seeing explanations, almost nobody trusted the model, and almost everybody got this no insight. So explanations are really useful for getting this kind of insight. Now, so far, I've been talking about explaining individual predictions. But we also want to understand how models are behaving as a whole. So you can think of explaining one prediction as describing the local behavior of a model close to that prediction. So if you have the whole space of data, and you have one explanation, you get an insight into close to that space. So what we're going to do is we're going to pick k predictions to describe the overall behavior. And it's imperative that those predictions are not redundant, because otherwise you're going to be explaining the same space again and again. So we want something like this, where we cover the space of data. The way we do it is via submodular function optimization. I won't bore you with the details, but I will give you some intuition. And here's the intuition. What we do is we construct a matrix of features and instances. Remember, we want to show particular instances to the user. And this matrix represents what the explanations are. So we're saying that John Christ explains the first document, for example. There are two pieces of intuition. One is that we want to pick representative explanations. So Christ, in this toy example, explains 4 out of 5 examples. So we want to pick an example that has Christ in it, because it's really important. But we also want to avoid redundancy. So if we pick this instance and this one, we cover 3 out of 4 features. But if instead we pick these ones, we cover 4 out of 5. And we're covering the 4 most important ones. This is the intuition for the submodular selection of instances. We evaluate this in a couple of different ways. The first one is we're asking people to choose between models. And this is a task that people in machine learning have to do all the time. You have a model in production, you have a new one. Which one is better? So we decided to ask people in Mechanical Turk what they thought. We showed them predictions from 2 different models side by side, and asked them to choose which model generalizes better. In this case, we know which one generalizes better. So we can measure how many times they get it right after seeing a few explanations. Here are the results. If they just guess, obviously they'll get close to 50% of the time they'll get the right one. If they use LIME, our explanation procedure, looking at random instances, they get close to 75%. But if they use LIME with the submodular procedure I gave you the intuition for, they get the right model 89% of the time. So these are people who have no expertise in machine learning at all. They just have some prior knowledge about the task. In this case, the task was atheism and Christianity again. If we pick based on accuracy, we would always get it wrong. So we made this example so that the model that generalizes better has lower accuracy on cross-validation. Now, obviously, the next test that we thought was, hey, can people on Mechanical Turk improve our models? Can they do feature engineering? So we have a data set, 20 news groups. I already told you about it. We have a test set. We train a data set, make predictions, and explain those predictions. We then show those explanations to people on Mechanical Turk and ask them to give feedback on the explanations. So we ask them to tell us which explanations do not make sense so we can clean our data. And we repeat this process again and again. And then we evaluate the models that we learn on a hidden data set that the Mechanical Turkers do not know about. So they can't be overfitting to this data set. They don't know we're training models. They only see a few explanations and click on words. These are the results. This is the interface that they see. Same thing, they see an explanation. They click on the words that they don't think are appropriate. So these are the results. We're measuring accuracy on the hidden set. If we just train the classifier on 20 news groups, we get really low accuracy, I told you before. If we clean the data ourselves, we're machine learning experts, we get close to 67% accuracy. This is the result for Mechanical Turkers after a few rounds. And they get really high accuracy, really high generalization accuracy. So they can do feature engineering really well. perhaps even better than us, which says something about Lime, I hope, more than about us. So in conclusion, I just want to end by summarizing that we have Lime, this new procedure that can explain any classifier. And it's really useful for the trust problem, figuring out if your model really works. It's also really useful for the related task of getting insights, figuring out what the model is doing. And with those insights, it becomes much easier to improve models, fixing them. And we have open source software. You can go and try it out. Let us know what you think. And I end here. Thank you.
So questions?
Hi, thank you for the talk. Are you doing any work to extend this to regression, to more than just classification tasks?
Yeah, we have been thinking about it. It's an obvious extension, and we are doing some work on it. And also other tasks like structural prediction, stuff like that.
Thanks for the very interesting work. I have more of a comment than a question. So European Union is bringing in a legislation where from 2018 they have a right to explanation. So the subjects, the people can reject any decisions made by machines if they don't get a good explanation. So I think your work will become very popular.
Thanks. I hope so. But yeah, I'm no lawyer, so I don't know.
Hi, I have a question. So in your slides, you perturb your representative sample in a certain way. So for different data modalities, how do you go about choosing the best mode of perturbation method?
That's a great question. And obviously, for every type of data, be it text, images, or speech, it's imperative for this to work that we find a representation that humans can understand, but also that when perturbing, we can get different things from the model. And we did something for images and for text that we think makes sense, but there's still some work missing in video or audio to come to those representations.
Hi. It's a very nice talk. My question is actually in two parts. Let's say the function that you are trying to approximate, it's called as f, and your approximation is g. Now I'm assuming that the domain of f and g are not same, right? Need not be same. And your perturbations happen in the domain of g, the approximation. So here is my question. How do you know, for example, that your explanations that are coming from g actually are the reason why f is going wrong?
Great question. So we can't know why exactly. Like, we can't know for sure. It's a black box. So the only way to know for sure for a neural network is to inspect the weights coming out of the neurons and etc. Right. What we have is an approximation. But we can measure our error, like every time we make a prediction, and we can measure the approximation error.
Right.
And if the approximation error is terrible, we can tell the user, look, we can't explain this particular example.
Okay. No, so my question was, have you evaluated your model such a way that the explanations that you receive for some bad decision have been corrected by looking at the explanation and then noticing that f has improved?
Sorry, could you repeat the second part?
My point was, have you evaluated your model in such a way that you look at the explanation that you get from the approximation, and then you figure out a correction for f, and then see whether that explanation that you got was actually the reason why f was wrong?
So we did some experiments with classifiers where we know what the explanation should be. So we took like really sparse logistic regression. We know what the explanation is, or we took a really short decision trees, and we saw if our explanations were corresponding to what those models were doing.
Right.
And I think that's the best we can do for those models. Okay. And our explanations did really well. Okay. I just didn't talk about it because of lack of time. Thanks.
Thanks.
All right. Due to time constraint, let's thank the speaker again. And if you have more questions, you can ask the speaker.